Chapter 4 is related to the correlation and convolution. This chapter discusses the calculation of correlation and convolution and some simple applications. At the end of the chapter, you will be able to compute the circular and linear autocorrelation and cross-correlation of the two sequences, compute or calculate circular and linear correlation or convolution using DFT, and perform fast convolution or correlation for very long sequences using two methods, overlap and add and overlap and save, and calculate the energy spectrum of a finite length signal from the oscillation function, and moreover use autocorrelation to estimate the period of a signal and cross-correlation to estimate the time difference between two signals, and employ autocorrelation to estimate the power spectrum of a random signal and cross-correlation to estimate where two signals are correlated. Now, correlation. If we consider two n-input sequences, x1 of n and x2 of n, their correlation is defined as follows. R12 is equal to 1 over n times summation n from 0 up to capital N minus 1, x1 of n times x2 of n. Okay. Now, very simple example. What's the correlation between two sequences x1 and x2, both having a test pattern 1, 2, 3, 4? Okay, very simple equation, and you'll get the result 1 over 4 times 1 plus 4 plus 9 plus 16, which equals to 0.5. Okay. That's a start, a very simple start, but it has problems and we cannot use it. Why? No. A shift in one of the sequences and we want to find the result about correlation. The next example. What's the correlation between two sequences x1, the same as before, but x3 a shifted, or better to say, a rotated sample, okay, 4, 1, 2, 3. So, the result is, of course, 6. But it's going to be meaningless. Correlation should be preserved. A shifted sequence is completely similar to the original one, but the result has changed. Okay. That's why we go to defining cross-correlation function. The next CCF, or cross-correlation function, is defined as follows. Now we add the parameter called lag. Okay, R12 of j is equal to 1 over n sigma n from 0 up to capital N minus 1, x1 of n times, here the new idea, x2 of n minus j, or maybe n plus j. Okay, here you see x2 n plus j could also be correct. J is called lag. Now, the third example. It's the cross correlation between two sequences x1, 1, 2, 3, 4 and x3, 4, 1, 2, 3. Simple computation. For j equals to 0, we'll get 6. Okay. J1, 5.5. J2 6, J3 7.5. Okay? What about J being equal to 4? The same result because it's a periodic answer. Okay. Now we want to normalize the results because a signal is similar to another 100% or 0%. How can we get it? A very useful equation. Rho of J is the same CCF divided by 1 over n times sigma n from 0 up to capital N minus 1 x1 to the power of 2 times the same idea about the second signal square root. Okay? Now the result is normalized. But in continuation, we will use CCF and ACF as well. What about the next idea? ACF. It is defined as follows. R double X of J is equal to 1 over n sigma or summation n from 0 up to capital N minus 1 x of n times x of n minus j, shifted version of the same signal. So we want to investigate its properties. Properties of ACF. Maximum value. Of course, it will happen for j being equal to 0, meaning that r double x of 0 is greater than or equal to r double x of j for any j. Okay? Power. The average power of a signal or normalized energy is equal to ACF with j being equal to 0. Okay? Power is equal to r double x of 0 being equal to 1 over n summation n from 0 up to capital N minus 1 x to the power of 2 of n. It shows power idea. Even symmetry. R double x of j is equal to r double x of minus j. Now, a very important idea similar to circular convolution. If you remember, we need to have augmented zeros at the end of the sequences. Okay? Similar idea. If the lengths of the first and second sequence is n1 and n2 respectively, then add augmented zeros such that their lengths be equal to n1 plus n2 minus 1. Okay? The result for circular, or it's called cyclic, of course, for circular correlation will be equal to linear correlation. Similar idea related to circular and linear convolution explained earlier in the previous chapter. Example. Find circular correlation of x1 of n being 1, 2, 3, 4 and the second sequence 5, 6, 7 test patterns. Answer. When we write down the first sequence 1, 2, 3, 4 and adding 2 zeros at the end, of course it's periodic, just a period has been picked. The next one 5, 6, 7, 0, 0, 0, 3 zeros. If lag is 0, the result will be 38. 1, 20. 2, 7. 3, 20, 4, 39, 5, 56, and 6, 38 RAB of J repeats because it's periodic. Okay. So final result will be 38, 20, 7, 20, 39, 56, a periodic sequence with a length of 1, 2, 3, 4, 5, 6, which is 4 plus 3 minus 1. The length of the first sequence plus the length of the second one minus 1. Right. The relation between cross-correlation and convolution. It's a very important topic we are discussing right now. These operations are similar to each other except that in convolution, the second sequence is considered time reversed, while in cross-correlation it is not. So, if we are interested in using DFT for autocorrelation or cross-correlation function, what will happen? So the next topic, computing CCF using DFT. Now, circular convolution of two sequences in time is equivalent to their DFT multiplication. Also, the effect of time reversal of a signal is equivalent to complex conjugate of its DFT. Consequently, finding the cross-correlation between two time functions or sequences is equivalent to multiplying the DFT of the first sequence by the complex conjugate of the DFT of the next one. That's the idea. Meaning that here you see a very important equation. Okay? Now, with this understanding, FFT can be used to achieve the goal. Take home. Write a program in Python to calculate cross-correlation. Verify the result. Okay? Very important task for you to be done. The next topic. Fast cross-correlation or fast convolution for long sequences, where it normally happens in factories, military industry, or anywhere else. Okay? Fast convolution method is often used to filter long data sequences. For this purpose, the data must be segmented, then convolution is performed with N2 sample impulse response to obtain the desired output. However, at the border points between the segments, N2 minus 1 sample value will also depend on N2 minus 1 samples from two adjacent segments. There are two methods to fix this problem. The first one is overlap and add. The next one, overlap and save. Note that with these methods, the first or last examples, output or samples in the output will not be valid. It's not important at all. This problem, it's not important because the huge amount of input information is streaming. So you will never see the first part of the input signal and output signal samples as well, and at the end, the same idea. Okay? On the other hand, if these two methods are not used, we have to wait for a long time to receive all the input information and then try to find convolution or cross correlation, which is impossible in practical environment. Okay? Because you need to have n of length of output is called ny is equal to nx plus nh minus 1. So you need to gather all information, then do some processing. Absolutely impossible. Okay? It means that it will not be possible to process it or even store data in terms of memory size. Right. Now we are defining overlap and add method. In the overlap and add method, the input x of n is divided into segments of length n1, and then n2 minus 1 zeros are added to the end of each piece. The length of h of n, which is called n2, is increased by adding n1 minus 1 zeros to its end, so that the length of both sequences will be equal to n1 plus n2 minus 1. Then the convolution of each part of x of n with h of n is obtained, and n2 minus 1 final samples of each segment are overlapped with the same number of the samples from the first part of the next section and added together to get the correct result. Otherwise, it will be wrong. Now you'll get the idea, don't worry. Find the convolution of x of n with h of n using overlap and add method. Let n1 be equal to 4 and n2 be equal to 3. Okay, x of n is a stream starting from x0 up to x11. Of course, in practice, it's a lengthy one, but we want to learn the idea. Okay, with h of n being equal to h0, h1, h2. Please write it down here, or later pause the video and carefully study the idea. Now the solution. For the first segment, where x of n has a periodic form of x of n being equal x0, x1, x2, x3, 0, 0, you know why they have appeared here, and again, repetition. 2 zeros added. Because the length of impulse response h of n is 3. Okay. Now we will have the first segment. x0, x1, x2, x3, because n1 has been chosen to be equal to 4. So 4 samples appear here. Now what about impulse response, h of n? h0, h1, h2. Now carefully look at it. Y of 0 is equal to needs x minus 2 times h2. So what will be here? 0. Okay, why? You see here, x0, x minus 1, x minus 2, x minus 3, x minus 4, x minus 5, x minus 6. Okay, so be careful about these 2 zeros, x minus 1 and the next one, x minus 2. Okay, so here we can write 0 times anything will be 0 plus x minus 1 times h1, which will be definitely 0, plus x0 times h0 based on the convolution equation. Okay? So y of 0 has been built. What about the next sample in output? Y of 1. You see here, x0 h0, x1 h0, x2 h0. You remember the definition of the convolution, of course. x3 h0. Now, here x1, x0, x minus 1, which is 0, will be y of 1. Y of 2. Here again, 0, 1, 2, 3. Up to here, everything is okay. And very simply, you can understand them. But you need to be careful about the fourth y of 4 in output. You see here the index 1, why it has appeared here. You'll understand it. Again, y1 of 4 is equal to x2 h2 plus x3 h1. It needs x4 times h0, but it doesn't exist in the chunk we have selected. Okay, it hasn't come yet. Okay, so it needs x for h0, but it doesn't exist. Remember it. Now the next, y1 of 5 will be equal to x3 h2 plus it needs x for h1, but it doesn't exist, plus x5 h0, again it doesn't exist. So missing parts. Okay, please remember these two samples. They need to be corrected later by the next chunk. Okay, hope that you have written them down. Now the second segment has just appeared. x4, x5, x6, x7. Again, impulse response. So here, y2 of 4 will be 0 plus 0 plus x4 h0. So y2 carries the missing information related to y1 of 4. Okay? If we overlap y1 of 4 with y2 of 4 and add the results, the correct y of 4 will appear. That's the philosophy of the method we are just defining. The same idea for y2 of 5, which will be 0 plus x4 h1. It exists, no problem, plus x5 times h0, no problem. y6 is okay, y7 okay, but y1 of 8, again, x6 times h2 plus x7 h1 plus x8 h0, but it hasn't appeared. Okay, so missing information. The same story for the ninth sample, if starting from 0, y1 of 9 will be x7 h2, it's okay, plus x8 h1, missing info, plus x9 h0, missing info again. Definitely the next section will correct it. Now segment 3, x8, x9, x10, x11. H the same, Now y2 of 8 will be equal to 0 plus 0 plus x8 h0. y2 of 9 is equal to 0 plus x8 h times h1 plus x9 h0. Now y10 is okay, y11 okay, y1 of 12 missing info, y1 of 13 missing info. Okay. Now correct output samples after overlapping and adding will be y of 4 will be y1 of 4 plus y2 of 4, and the same story for y5, y8, y9. But what about the last samples? y1 of 12 and y1 of 13 will never be correct. The output samples y12 and y13 will not be corrected. Never. Because we have reached to the end section of the stream. It's not important in a real situations where the input stream is a lengthy one. Okay. Now the following program in Python is about the overlap and add method, a very important program. We are just going to run it now. We will run a overlap and add. You see here, x of 1 is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 as a test pattern. H of n has been selected to be minus 1, minus 2, minus 3. The result using linear convolution is minus 1, minus 4, minus 10, minus 16, minus 22, minus 28, minus 34, minus 40, minus 46, minus 52, minus 58, minus 64, minus 57, minus 36. But the result obtained by the method we just defined, overlap and add method, will be the same up to minus 64. The last two samples will not be computed. So here we have shown the difference between the results of y linear and y overlap and add. Going back to lecture note. Okay, the same coding. Now, okay. Here you see if is numpy dot sum mp dot apps of y linear from 0 up to nx minus y of overlap, and the results show that there is no difference between the results. Okay, now evaluate the program for different inputs and impulse responses. Just leave test patterns. 1, 2, 3, 4 is not a complete idea. Just choose a cosine input and then any impulse response you wish, and then run the program and report the results. And another oral take home: do the same job for correlation. Okay, we did it for convolution. Now it's your duty to write down the coding for correlation using the ideas just explained.